let us finish this session quickly. In the previous session, we discussed about the curvilinear trend, and a special trend line fitting was discussed, which is called second degree parabola fitting. Another trend line fitting is also sometimes taken into consideration, and this is known as, this is also non-linear fitting, and this is called fitting of exponential curve. Fitting of exponential curve. So first of all, what happens is that in this type of analysis, we have to identify what sort of equation that we are going to select. What is the form of the equation? Once the form of the equation is designed, then we have to do the calculation to find the parameters and hence the curve. So this job is not that simple as it seems to be, because once a big data is presented in front of you, then whether a linear fitting will be the best fitting or a non-linear fitting will be the best fitting, that we don't know. If the linear fitting is best, then it is okay, the job done, we can find it out. If the non-linear fitting is the best fitting, then the things become pretty much difficult, because in this case we do not know what sort of non-linear fitting will be better. Will it be an exponential fitting, or will it be a second degree parabola fitting? Will it be a power curve, or will it be a logarithmic curve, or will it be a Gompertz curve? Many other different curve fittings are there, but in this particular space of your syllabus, only two types of non-linear fittings have been retained. One is second degree parabola fitting, and another is exponential fitting. So I am going to finish this topic, and this topic is from unit 5. Remember, it is not from unit 4 that I'm discussing right now. I'm going to finish this topic of curve fitting with the discussion of fitting of exponential curve. No other fitting will be taken into consideration. To fit the exponential curve, we will first select an equation of the given form. First, we'll say that, okay, let this be the curve which is best fitting our given data. Okay, this is an exponential curve, and this curve, or sometimes we can also go for rather this curve which I'm considering over here, it is sometimes also known as power curve. Okay, and if you want to go for the exponential curve, you can consider a little bit different form, which is given as this. Then that would be a correct representation of the exponential curve, you think. Because you may think that sir is saying sir is mentioning the word exponential, then where the exponent, where the exponent is, where e is. So this sort of curve is called a power curve, and this sort of curve is called exponential curve. But I'm considering them together because the analysis part of these curves, the approach of analysis for these two particular curves will be similar. So first of all, let me talk about what will happen if we consider the power curve, how to analyze it. And similar approach can also be designed for, can also be thought for the exponential curve. So if you think that is not mentioned by any teacher, they often forget to mention it in the classroom. This word I'm saying, if you think that your data is best fitted by exponential curve or power curve, and you are choosing the curves accordingly, then you will find that in this curve we have got a non-linearity of this form, where the constant has been raised to the power x, and it is very difficult to analyze such a kind of curve, and it is very difficult for us to find the normal equations if the x is retained in the power of the constant. So what you want to do in this particular case, we want to uh, bring the power, bring the x down from the power, and then we can analyze the situation quite easily. And that can be done by taking logarithm on both sides. So in this type of cases, what we do, we take logarithm from both sides, and after this what we get? We get log y, log of a b to the power x, which is equal to log of a plus log of b to the power x, and that is equal to log a plus x log of b. Now the base of this logarithm can be considered to be 10. No problem with that. Any base will do. Any base will work. There is no special reason for choosing a base. Why base is choosing? Because the base is the number system with which we actually numerate things. We have 10 fingers, so we'd like to use the base 10. If you want to use the base 2, then actually you are thinking of binary system. The result will be different. Sometimes you can choose the base to be e, so you can choose any base according to your choice. But once we do, what happens is that you try to look at this quantities. What is this? What are these quantities? It is log a to the base 10 and b to the base 10, and we can replace this quantity by a term called capital A, because you know that this term is constant. Once small a is known, but in this particular case, what will happen is that is this small a and small b are unknown. So since small a is constant, you can name logarithm of a base to 10 is also constant, and therefore we can put another notation for this, where we are choosing capital A. Here we are choosing logarithm of b to the base 10 as capital B, and this term you can consider as capital Y prime. Now what we are doing, we are getting several new quantities. Y prime, which is actually equal to log y to the base 10, and capital A is log of a to the base 10, and capital B is log of b to the base 10. Only thing that is not changing is x. X is remaining as it is. Okay, x is retaining its original nature. Now, although you carefully observe that although this is some kind of non-linearity, but what we have obtained over here is a kind of linearity in terms of y prime and x. If you want to rename x, you can rename it as x prime if you want. Okay, if you can write it as x prime. Only thing you have to write over here, note down that x prime is equal to x. So you can say that y and x are non-linearly connected, but y prime and x prime equal to x are linearly connected. Okay, and once they are linearly connected, because they are related to one another by linear equation, immediately what you can do, you can form two normal equations. So your first normal equations will be summation y prime is equal to n into capital A plus b summation capital X prime, which is obviously equal to x. And second, what you can do, you can multiply both the terms by x prime, and you can write it as x prime y prime is equal to a x prime plus b x prime squared. Sorry, prime is there, x prime squared. Now we are going to solve this equation, solve the given equation for capital A and capital B. And from this linear equation, we will be able to find capital A and capital B pretty easily. Now, once we find capital A and capital B, so but we are not actually interested about capital A and capital B. We are interested about small a and small b. So from there, you can find that if capital A is logarithm of this quantity, so small a will be antilog of capital A. And if capital B is logarithm of small b, so small b will be the antilog of capital B. So once capital A and capital B found, from there we can easily find what the value of small a and value of small b. Once these values of small a and small b are obtained, we put these values over here. And we get our required power curve. Also, you have to keep in mind that when we try to solve the linear equation in terms of y prime and x prime, we have to form our table accordingly. Remember, initially we had capital X and capital Y. Some values of capital X and their corresponding value of capital Y are given. We want to fit the curve. Okay. Now, since they are given, what we actually do, we are not solving the equation. We are not solving a linear equation related to x and y. We are solving the linear equation related to x prime and y prime. So what you are supposed to do over here is that you will again write x prime. Here you remember that according to your choice, x prime is equal to x. They are same. So you are just copy the value of x over here. You are going to choose the value of x over here. Okay. So x prime is similar to x. Then what you need to do is that you need to calculate y prime. And y prime is the logarithm base 10 of your values of y. So we are going to calculate this also. And then you are going to calculate the quantities which are there in the normal equation. In the normal equation, we have x prime squared, which is equal to x squared in this case, and we have x prime and y prime. So these values will be calculated accordingly, and their summations will be obtained from the table. And accordingly, what we can find capital A and capital B, and we can proceed with finding the power curve to the given set of data. I ask all of you to take a screenshot of this particular page, because I'm going to move on to the next page. What happens when the curve is exponential? Similar approach will be applicable over here. When the curve is exponential, that means your equation is a e to the power bx. But here, since you have considered this exponent e, remember in this particular case, you are going to take the natural logarithm. Taking natural logarithm on both sides, we get ln y, which is ln a plus bx ln e. But ln e is equal to 1, and therefore this would be equal to ln y ln a plus bx. So here a little bit of difference is there if we compare this curve and that curve. Okay, what are the changes that has been made over here? We can re-represent this in terms of linear equation. We can consider this to be your y double prime, this to be your capital A1, and you can write it as B1x double prime. So what are the changes and what are the things that are remaining same? X is same as x double prime. Y double prime is actually your natural logarithm of y, and a1 is equal to your natural logarithm of this constant small a. b1 is same as b. Okay, and once you get this, immediately you can form the normal equations. You can form the normal equations, and the corresponding normal equations will be y double prime is equal to n into capital A plus b1 into summation x double prime, and both the sides will be multiplied by x double prime, and we'll write it as a1 x double prime summation x double prime and b1 summation x double prime squared. Okay, and this equations will be calculated for a1 and b1. These values will be obtained as before, and by taking the anti-logarithms, we will find small a and small b, and that can be replaced over here in this equation. Okay, so in this case, we can actually consider, oh, one more thing. Make sure that whatever is there in this particular normal equation, similarly, you have to construct your table. As per the requirement of the equations, you have to construct the table just as I have shown over here. So in this manner, we can fit a trend with respect to power curve and exponential curve. But what is the basic hidden criteria that we are maintaining in all of these things, all of these kind of relationships? The hidden thing is that some kind of, we want to, although the curve is non-linear, we want to bring some sort of we want to extract out some sort of linearity from it, and we want to try to analyze that hidden non-linearity inside the hidden linearity inside the curve, because direct non-linear trend analysis is not possible in this particular case. So we are going a kind of roundabouts to come to our to get our given curve that we want to fit to the given set of data. So with respect to the I ask all of you to take a screenshot of this page, because I'm going to stop the share right now, and I want to check the problem which I considered in the previous case, that where I fitted the second degree parabola and the cubic polynomial. I want to check what sort of curve that particular data is showing with respect to exponential and power curve. So I'm going to do it right now. So I'm stopping the share, and let me share the previous screen, the Excel sheet with you. So that was the Excel, that was the data which we had. Let us delete this particular curve because this is not required anymore. We have this data, and first of all, let us draw the scatter diagram afresh. So this was the scatter diagram. Okay, now we are going to select these points and add the trend line. Now we have exponential button, we have power button. Let us try to check what comes out of it. So if I try to select the power button, and if I use it, then this is the curve that will be obtained for the given set of data. So for the given set of data, you can also use the exponential curve, the power curve. I think as the curve which actually we obtained for the second degree parabola for the, no, it is not, yeah, for the second degree parabola fitting, the curve that we obtained was like this. Okay, so we are going to fit the second degree parabola once again. Let's see. This is the linearity. Okay, I'm choosing polynomial. So this was the polynomial that we fit over here. And if you want to fit this exponential curve, let us try to look at what comes out of it. Okay, just a minute. Yeah. So if I want to fit exponential curve, let us try to check what comes out of it here. So you are going to select the exponential button now and see this is the curve which we have. And if you want to select the linearity between them, then let us keep the linear figure in front of us. Why it isn't coming? Yeah. Just a minute. Yeah. So just see that all the curves for to the give, what I wanted to show to you is that all for the given set of data, all the possible curves that we have imagined has been fit to the given set of data. And after if you look at these 4 figures, what is our analysis in this particular case? Our analysis is showing that if I look at this second degree parabola, you see none of the points are falling on the curve. None of the points are falling on the curve. So I think, in my opinion, the second degree parabola in this particular case will not be a best fit. So I shall reject it. Second degree parabola will be rejected. Okay. If I try to compare this linear curve and this power and exponential curve, what we come across is the following. First of all, try to look at the linear curve. You see, these 2 points are pretty much closer to the linear line, and this point also. This is somewhat little bit away, and other points are not falling apart. But if I look at this, then these 3 points are falling on the curve and very much closer than the linear curve. So, and if I look at that, then I'll see that here also the 3 points are pretty much closer to the curve than the linear curve. So linear curve linearity, this particular fit will not also be very good one over here. Now, if I want to fit, if I want to compare the exponential curve and power curve together, let us try to analyze that which one is the best fit. So in my opinion, and I think your opinion will be also like that, I think this exponential fitting is pretty much better than the power curve fitting, because just look at the points, the position of the points with respect to the curve, the occurrence of the points with respect to the curve in this diagram, and occurrence of the points with respect to the curve in this diagram. So I think if you ask me that what sort of fitting you are going to approach, you are going to take over here, I'm going to say that yeah, I'm trying to take the option for exponential curve. But that will not be a very mathematical approach, because the perspective, my perspective and your perspective can be different. So if you want to test it mathematically, at least what you can do is that once we find these equations, what we can do is we can write the estimated value. We can write the estimated, sorry, it is not, just a minute. Linear fitting was, oh, sorry. I wanted to show the equation with respect to the exponential curve. Okay, so if I want to fit the linear curve, then exponential curve, I have got the exponential equation and we have the power equation. What we can do here is that we can estimate the value of y. How many x and y's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 values are there. We can estimate 10 different values of y with respect to power curve and 10 different values with respect to the exponential curve from the equation. We can find out the difference of the original value of y and the estimated value of y from the power curve, and we can take the difference of original value of y and estimated value of y from the exponential curve, and then we can compare the difference, and we can if the differences are pretty much haphazard, we can find out the average difference of the two columns, and the least average difference corresponding with the least average difference, I am going to consider that particular curve to be the curve of best fitting to the given set of data. So in this way, we can analyze, we can fit different curves to the given set of data, and it is called curve fitting. And all these actually that we have done today are actually fall under the category of curvilinear regression. We are doing regression analysis, but not the linear regression has been discussed. A curvilinear approach has been discussed in today's class. So with this, I'm going to conclude my today's session, and I hope I am able to make you understand the pros and cons about this regression analysis. Many more things are yet to be discussed, which are not directly mentioned in the syllabus. But if I keep on discussing on regression, then other things that are still remaining to be discussed, will not be having time to discuss those important issues. So with this, I'm going to put curtain down on the chapter of regression, but it is not down for you. You are going to study and do the problems by yourself to get a better hold of this particular regression analysis. You can also do some sort of online courses, because your MOOCs course is also there now, for which the marks are the coordinator is going to upload the certificates. So you can do some kind of MOOCs courses on regression analysis. Some good courses are there in the Knockout basket. I'm talking about Coursera because nowadays NPTEL is stopped because of this COVID situation. So if you do not have any problem, you can go for this kind of massive open online courses on regression analysis. So with this, I'm going to conclude my today's session. Hope you have enjoyed, and tomorrow we are going to meet at 8 p.m. once again. Till then, bye.